Thank you. I'm going to wait a few seconds while I hope this PowerPoint doesn't crash and it actually comes up with unbelievable. Unbelievable. Come on. Oh, okay. So here's where we were in the last few classes. A quick recap, we saw that neural networks were universal approximators that can approximate any function if they have sufficient architecture. But then, given a network with sufficient architecture to make them approximate a function, we had to estimate the weights and the biases of the network to make the network approximate the function. So the way we did it, for any setting of weights, the network will you have some target function d of x. For any setting of weights, the network will produce some output function f of x. The semicolon w means that the w are the parameters of this function f. And so we defined a divergence function, which was the difference between f, which is the actual output, and the d, which is the targeted output at each time. The divergence function had this property that it's always positive, and it's 0 if f is exactly equal to d. Specifically, we like to make the divergence function differentiable. What we mean by differentiable is that we should be able to quantify how a small change in f changes the divergence itself. We'll see why this is important. We also made all of the activations of the neurons differentiable. That way, we can compute how a small change in a parameter changes the output of the neuron. We chain it down, we can compute how much it changes the output of the network itself, and in turn, how that changes the divergence. And we could use that to figure out how to adjust each of these parameters. That lets us optimize the network. And now that we have defined a divergence, we can define the expected divergence as this between the actual and the desired output of the network. The expected divergence quantifies the area shown here in gray, and we estimate the network parameters to minimize this expected divergence, ideally. The problem, of course, is that in order to compute this expected divergence, you will need the function d of x, shown in red over here, at every location of x. And we usually will not have that information. So what we do is to draw a bunch of training samples, and where each training sample consists of an x value and the corresponding target value, the value of the function that we are trying to model. And so these xd pairs form our training instances. We instead of computing the expected divergence, which is this shaded area over here, we now approximate the expected divergence as the sum of the divergences at each of these training instances, basically, or the average of the divergences at each of these training instances, basically the average of the lengths of these lines. So this forms our loss, and this loss approximates the expected divergence. We estimate the network parameters to minimize this loss instead. And so here was our final problem statement for the neural network. We are given a training set of input-output pairs. We construct our loss function as the average divergence over the training set. So once for a given training set, the x's and the d's are all specified. So now this loss function becomes a function of only w. And then we minimize this loss function with respect to w. This is a problem of function minimization, which is an instance of optimization. This is where we stopped in the last class. Does anybody have any questions at this point? Anyone?
There are no questions on chat.
Okay, perfect. So what I'm going to do now is to quickly go over the basics of function optimization. Before I do that, how many of you understand what is meant by a derivative? Raise your hands. So almost everybody thinks they know what a derivative means. So I want one person to tell me, first lower your hands, and I want someone to tell me what you think a derivative really means. Anyone? Are there any answers on chat? What does a derivative mean?
Someone says best local linear approximation.
Best local linear approximation. Is that what a derivative means? It's close enough. Anybody else? So you guys, we have been through school and college. You should know, right? Anyone?
Gradient of a function, rate of change, slope of a function. A lot of people have their hands up as well.
Okay, so rate of change, right? Now here's the rate. Here is in a mechanical way. Here's the only way to really define a derivative. Okay. Suppose I'm going to draw this for a scalar function. I have some variable x. I have some function f of x. That function takes some value. At any point x, if I take a small step, tiny step delta x in the forward direction, this results in a corresponding tiny change in the value of the function itself, which is delta of f. And the derivative is strictly defined as the linear relationship between these two guys. So we have, if I define the derivative as alpha, then the derivative is, if I represent the derivative as alpha, the derivative is defined as the linear multiplier to delta x. So which is alpha, that gives you delta f. So it is the multiplication factor by which you multiply this increment in x to compute the corresponding delta of f. This is the only true way of defining the derivative. There is no other definition. Now, this is, of course, as several of you have pointed out, this is, of course, based on the fact that for smooth continuous functions, at a fine enough resolution, if this delta of x is small enough, the curve is going to be essentially planar. It's locally linear, and so this is based on this fact. But the definition of the derivative itself is given by this term. Now, how does this relate to things we do? So when x and y are scalar, remember that our functions can be vectors. X could be a vector, meaning it could have only one component, or it can be a scalar. It could be a scalar, meaning it has only one component, or it could be a vector with many components. Similarly, f of x could also be either a scalar or a vector. Now, we're going to focus on the case where f of x is a scalar, because when f of x is a vector, it's basically a very trivial generalization. I will get into that as well. Now, when x is a scalar, I can write delta of x as some increment d of x, and alpha is my derivative, and that gives me the corresponding change increment in f, which is d of f. Which is why now, obviously, when I write it this way, alpha is going to depend on the location. So here, for example, a small change in x results in a very different change in f than a small change in x at this location. So the correct representation, of course, is going to be alpha of x dx. This is for the case of a scalar. Now, if x is a vector, does anybody want to guess how that would change? So by the way, so only in the scalar case, you can write it this way. Because of this relationship, I can write alpha of x equals df over dx. Now, does anybody want to guess how this changes when x is a vector? Anyone? Any guesses?
Someone on the chat says derivative would be a vector.
Why?
Well,
Anybody?
because you have a coefficient for each input, right? So then you
Why?
have, okay.
So, I mean, you are giving me a mechanical answer, right? But okay, so let me give you a different question. If x is a row vector, what is the shape of my derivative going to be?
Still a row vector.
Why is that?
Because you need, in every direction, the value is changing. So you
But
got the row vector.
how did we define the derivative?
I guess the change rate.
Look at the screen. Okay, let me draw this, right? I have x, but now in this case, x is a vector. So x is the form x1 through xn, yeah? And f, of course, is some value, f of x. So what was our definition of a derivative? I just wrote it. Anyone?
That's the change in delta and y is equal to alpha times the delta and x.
Okay, so delta f equals alpha times, this is big equals alpha times delta of x. What is the shape of delta of x going to be? X is a column vector. What is delta of x going to look like?
Is it n by 1?
It's also going to be a column vector, right? So I have delta f equals alpha times delta x1 through delta xn. So this represents a small increment in x. You're trying to say, I have this small positive increment in x in every direction. And what is the corresponding change in f going to be like? So now f is a scalar. So what's delta f going to be?
Also a
Okay, now look at this equation. Tell me what is the shape of alpha?
It would have to be the transpose of the shape of delta x.
Exactly, and that would be
1 by n.
Yeah,
1 cross n. The derivative must be a row vector by the definition of the problem, right? And so over here, when x is an n cross 1 vector, then alpha of x is going to be an 1 cross n vector, and delta f is going to be alpha 1 through alpha n times delta x1 through delta xn. Now this is something that you just have to remember, because this is going to keep coming back. I mean, we just go through these notions of derivatives and we sort of blindly swallow anything that is given to us. But you stop and think about it, this is the definition. This is how you define the derivative. So alpha is going to be this row vector which multiplies the small increment in x to give you the corresponding increment in f. Now, here's something. When I increment f, so this of course also gives you back the original statement we made, right? Which was that someone made. I had delta f equals alpha 1 through alpha n of delta x1. This is supposed to be my delta xn. I'm really bad. I've got a chicken scroll for handwriting, so bear with me. This is not a 0, this is a delta, which means that delta f is going to be alpha 1 delta x1 plus alpha 2 delta x2 and so on, right? Now, I just said delta x was the increment in x. The only requirement I had was, in fact, I had no requirement, right? Delta x is any odd increment in x, which means I can decide what delta x is going to be. Now, if you're working in some n-dimensional space x1 through xn, and if I'm at some location x, my delta x could be in positively any direction at all. right? So in this case, I can make the choice that I'm going to choose a delta x, which is of this form, where I only increment the first component and the rest are 0. In this case, what is delta f going to be, given this formula? What would that be? Anyone?
Alpha 1 times delta x1.
It's going to be alpha 1 times delta x1. And so alpha 1 is the partial derivative of f with respect to x1. It is the multiplicative factor which tells you how much f is going to change by when you take an incremental step only along that direction and do not change the other values. So this is basically the very definition of how we define our derivatives. Alpha is going to be a row vector, which gives you this solution. The partial derivative alpha I gives us how y increments when only xi is incremented. And in that case now, you can, so going back here, what is the problem with this notation for the derivative, dy over dx? Anyone? Yeah?
That's not a partial derivative.
Does it work for x being a vector? It doesn't, right? You cannot write this thing. So this is really bad, poor notation. You're better off representing it as f prime of x because it captures the dependence on x. Also, the only correct definition for way of writing the derivative is literally this. You want to write, if you want to represent a derivative, then you want to basically use this notation, which is dy equals derivative dx. And when you say derivative equals dy over dx, you're making many, many assumptions, primarily that x is a scalar. But if you want to write it generically, this is the only valid notation for derivatives. Okay? So you see where this equation comes from, and way behind. Anyways, yes, Uma?
What are the assumptions you're making when you write it in the second way you had in the previous slide?
So when I write dy over dx, if x were a vector, can I write 1 over x? Can you cannot invert a vector, right?
Mm-hmm.
So you can multiply vectors, you cannot divide by vectors. So you cannot write 1 over dx or 1 over x. So you cannot write dy over dx. It only works when x is a scalar.
Okay, thank you.
Right? So, okay, now, so this is the derivative. Yes, there were a couple more questions. Yeah.
Professor, I have a question. So dy over dx, it's a notation, right? D over dx is treated as an operator, which is the derivative operator, and it's not like
No,
just the vanilla definition of division.
It's pretty much the vanilla definition. If you go back to your basic definition of derivatives, you're literally dividing the increment in y by the increment in x. It's not just mildly an operator. So when you want to write it as an operator, there are many other notations.
Okay, thank you.
Right? You go back to school. It's f of x plus dx minus f of x divided by dx. Remember that?
Yeah.
Yeah. So that's why.
Okay.
Anyway.
Okay, thank you.
Now, we've all heard the term gradient. This is not the gradient. The gradient is the transpose of the derivative so that it aligns up with x. Anyway, going on, I'm going to generally talk about optimizing functions because this is what this lecture is all about. And when I'm optimizing a function, I'm going to be optimizing some function of x. Yes. There's a poll. So obviously, we just said it, right? If y, you haven't been paying attention. If you said the derivative was anything other than a 1 cross n row vector, because when y equals f of x and x is a column vector, y is a scalar, then x is n cross 1, then clearly the derivative of y with respect to x is going to be 1 cross n. It's a transpose, because the product of the derivative and dx must be a scalar. Now, I'm going to be talking about generally optimizing a function of x with respect to x. So I'm speaking in generalities, not specifically about a network. The problem of optimization is typically the problem of finding a minimum or maybe a maximum. You have functions of this kind, some function of x, and our task, if we are trying to minimize the function, is to find the location where the function is minimum. So for a scalar function, a function of a scalar variable, the function would look like this. You want to find this location here. If it's a function of of multivariate inputs, then the input space itself is multidimensional, and the function has some minimum in that input space. We are trying to find this location. For this bowl, you're going to try to find this dot here. This the location of this dot where the bowl is a minimum. For this uglier function, you'd be trying to find this location here, where the function is a minimum. Now, you all recall how we computed the minima of functions in school. You had some function. Now, the property of a minimum was that as you walked away from the location of the minimum, the function always had to increase, otherwise it's not a minimum. So on one side, as you approach this x, the function is always decreasing. On the other side, as you go away, the function is always increasing. At that precise location, the function is going to be flat. So this was the criterion that we used to find minima. The derivative of the function is going to be 0 if it's continuous and smooth at the minimum. And so we just equated the derivative to 0, solved for the x that gave you this property, and that was the location of the minimum. Was that sufficient? Just equating the derivative to 0, was that sufficient? Anyone?
No, it might find a local minima.
Was that the only problem?
No,
Now,
it
when
can.
you find the second derivative,
Because both maxima and minima have 0 derivatives. These are what are called turning points. Why is it turning? The function is turning at these points. And so both maxima and minima are turning points. And what happens is that in the case of maxima, the function goes from increasing to decreasing. So the slope goes from being positive to negative. In the case of minima, the function goes from, this is the poll results, okay. In the case of minima, the function goes from decreasing to increasing. So the slope is initially negative and then it becomes positive. And so at the specific minima or maxima, the slope itself is 0, but in both cases, the slope is 0. What we observe is that the derivative itself has a negative slope at maxima because the derivative has gone from being positive to being negative. At minima, the derivative has gone from being negative to positive, so the derivative has a positive slope. And so if you compute the derivative of the derivative, we found that it would be negative at maxima and positive at minima. And so the way we solved for minima was that first we found the location where the derivative was 0. This could be a turning point. Then you check the double derivative, the second derivative. And if the second derivative is positive, then the solution to this equation was a minimum. Otherwise, it was a maximum. This is what we did in school, even if you have forgotten it. Now, the issue, of course, with derivatives is that derivatives can go to 0 at very many locations. So let me draw a couple of functions and let's see how this works. Say I have this is x, and I have a function which is like this. right? Then what is the derivative going to look like at this minimum? The derivative is going to look like so. Over here, the derivative is negative. So the derivative is going to be on this side here. Here, the derivative is positive. It's going to be here. The derivative is 0 here. So the derivative is going to be increasing at the minimum, right? If I have a function which looks like this one, then the derivative is going to be it's going to be positive out here. It's going to be 0 here. It's going to be negative out here. So the derivative will go from positive to negative. What about if I have a function which looks like this? Like this. What will the derivative be like out here? What's the derivative at this point? Anyone?
0.
0. And what is the derivative curve going to look like? Anybody?
Like a parabola?
It's going to be pointing upwards or downwards.
Like a hump, like a hill. But
It's going to be a book. Yeah, it's going to be a bowl, right? Because the derivative is positive out here.
Yeah.
The derivative is also positive out here. So the derivative is going to look like so. The fact that so now the fact that the derivative is a minimum over here didn't tell you anything. What does the second derivative look like? For this guy.
Straight line increasing.
So what is the second derivative going to be at this point?
0.
0, right? So here you have a situation where the derivative is 0 and the second derivative too is 0. In that case, you're likely to have a condition of this kind where the function is increasing and pauses and then continues to increase, or it's decreasing and then it pauses and continues to decrease. So these are what are called inflection points. These are turning points. These are inflection points. And the second derivative is going to be 0 at inflection points. So simply checking the second derivative may often not be sufficient. And for more functions of more variables, it gets much more complex. There was a question. What was that?
I feel like there's a few conditions necessary for that last.
There's several conditions necessary, because if if the thing flattens for a long time and then changes in the right direction, you could get
right.
You'd have to. The second derivative would be 0. You'd have to go and check the third and the fourth and the fifth derivatives till you found something that gave you a signal. You probably remember that from school, right? My point was that simply checking for a turning point is not enough. Checking for a 0 derivative is not enough. Checking for the second derivative is not enough. You often really don't know. Now, if I have a function of multiple variables, the optimum is still a turning point, which means that if I'm out here, at this point, the function is locally flat. So taking a tiny step in any direction will not change the function. And so our job for functions of multiple variables is also to find the location of the function where the derivative, which is the entire row vector, remember, for multivariate functions, you want every component of that row vector to be 0. That's when you know that you're likely to have hit a local minimum. Now, there's a brief note on the derivatives of multivariate functions. Maybe you already know the answer to this. We've seen what the derivative, how we define the derivative of a multivariate function. If x is of this kind, x1 through xn, then I'm going to represent this like so, and y equals f of x. Then I'm going to say the derivative of y with respect to x, that's my notation, I'll use it again, was this vector, right? Some, let me call this alpha, the partial derivatives, x1 y over xn. And the transpose of this guy is what we call the gradient, which was delta, sorry, partial y over partial x1 through partial y over partial xn. Does anybody know what this actually means physically in terms of the function? This is also a vector, right? This is vector. This is a vector in. This is in n cross 1. So this is also in n cross 1. What is this one? Anybody know? Okay.
N?
Yeah, go ahead.
N by N?
No, it's n cross 1, but physically, what is this? What this represents this also represents a vector, right? And so this vector has a direction and a length.
Professor,
This is so what do those mean?
it's the maximum change.
It's the direction of the, what do you mean by maximum change?
Maximum change of y vector.
So it's the direction in which the y is a scalar. It's the direction in which y changes fastest. You're absolutely right. So again, going back, we had df equals derivative times dx, right? This guy is a row vector. This guy is a column vector. So df is the inner product between your derivative and the increment of x. Clearly, this we know because I have my derivative equals this row vector, my increment equals this column vector, and so the transpose of the derivative is the gradient, and so df is going to be the inner product between my derivative and dx by definition. Now we know this property of inner products. If I have two vectors x and y, or let's say if I have two vectors, say a and b, right? So the inner product is of course a transpose b, which is the component wise a1 b1 a and bn, right? Now what is the actual, there's a different way of defining this. How many of you remember this? A dot b equals mod a mod b cos theta. You remember this? Anyone? How many of you don't remember this? Raise your hand. So if I have a vector a, if I have a vector b, the inner product, yes, Devdas? Okay.
Nothing, sir.
Okay. So the inner product is going to be a function of theta, right? And specifically, the inner product is proportional to the projection of b on a. So when will this be maximum? At what angle? What must the angle between a and b be for this inner product to be maximum? Anyone?
0.
0, right? So a dot b equals max when implies theta equals 0. When is it going to be minimum?
90.
You're speaking of minimum in magnitude.
What is it going to be? Oh, 180.
Exactly. A
Okay.
dot b equals min when theta equals 180, right? Now go back here. So remember when we were trying to, where is my mouse? So remember, my derivative is a vector, right? So in my input space, x1 through xn, these are my components. At any location, my derivative is also going to be a vector in this space. And the increments that I take at this location, when I decide to take an increment delta x, I could take the increment in pretty much any direction. The property that we had, which said that delta y equals the derivative times delta x, this should hold regardless of which direction I'm taking my step in. But then depending on the direction in which I take my step, the change in delta y, the increment in y is going to be different. When will it be maximum? Anyone? So when's that going to be
When they
maximum?
align.
When they align, right? So when delta x is exactly in the direction of the gradient, that's when the function increases fastest. When delta x is exactly opposite to the direction of the gradient, that's when the function decreases fastest. And so basically I have this little animation over here which shows this is my my derivative by gradient actually. And this arrow shows different directions in which you could be taking a step. And this shows you the resultant change in the function itself. And you can see that when the step is exactly in the direction of the red arrow, that's when the change in the function is maximum. And when it's exactly opposite, that's when the change in the function is maximum, but in the other direction. So the gradient is the direction of the fastest increase of the function, which takes us to this property here. The gradient vector is going to be fastest. This is the gradient vector. Moving in this direction increases f of x fastest. Moving in the opposite, minus of the gradient, decreases f fastest. And of course, at the turning points, the gradient is going to be 0. There's another property that that the gradients have, which we use all the time, which is this: that if I have some function, some kind of a function, which is a multidimensional function, I can slice it at any point. If I slice it and knock all of these off, then I'm going to end up with just this edge, right? Because the upper portion has been sliced off. And the gradient is going to be, now the gradient is actually a direction in the input space, right? The gradient is always going to be perpendicular to this edge, to the level set. That's just a property that gradients have. We won't get too much into that right now. So there's a second characteristic of these multivariate functions called Hessians. The Hessian is a matrix of second derivatives. So the ijth component of the Hessian is the derivative of the function with respect to the ith and the jth components of x. So this guy is the second derivative with respect to x1. This is the derivative with respect to x1 and x2 and so on. This will be symmetric. This quantifies the second how the gradient itself changes. I won't explain it, but we will use it. Now, here's another property that you might find very useful. In fact, we're going to encounter it again. Now, we found that, here's what we found. We found that when I write y equals f of x, and if x belongs to n cross 1, then we found delta y equals whatever f prime, I'll write this as f prime of x, which belong to 1 cross n, which is the same space as the transpose of x. Now, if y is a vector, then y is going to be y1 through yn, right? And so, if you look at what the derivative of this vector of y is going to be with respect to x, it's simply y itself is a stacking of many components of y. So the derivative of y is going to be a stacking of many 1 cross n vectors. Basically, an identical stacking of the derivatives of these individual guys, which is going to give me, if this has, say this is yn, this is going to give me an m cross n vector, which is called the Jacobian. You have encountered this in the past. If you haven't, we'll see it again in the next class, not in this class, okay? And now, if y is a matrix and x is a vector, then this is going to be a matrix-like arrangement of n cross 1 vectors. It's basically the derivatives of y with respect to x is going to be the derivatives of the individual components of y stacked in exactly the same way. as the components are stacked within Y itself. Anyway, returning to our problem, the optimum point is right. So clearly the third one is the correct answer. You're trying to find the maximum decrease. You want to minimize f. For maximum decrease, you must walk exactly opposite to the gradient. Anyway, if I want to find the minimum of a function of a multivariate input, I must find the turning point where the gradient is 0. But then I also have to check the Hessian. And just as the second derivative is negative for scalar inputs, when the input is a vector, the second derivative is, the second derivative is positive at minima for scalar inputs. For vector inputs, the eigenvalues of this Hessian are all going to be positive at a minimum. So one check is to find out the location of x where the derivative is 0 and where the Hessian is positive definite or positive semi-definite. We'll see that later. Anyway, the problem is if you want to just, if I give you a function and I ask you to find the value of x where the function is minimum, you can try to solve for this. Try to find where the derivative is 0 and where the Hessian is positive, positive definite. For this, you need f to be in some kind of a closed form. For something like a neural network, the function is hideous. There's no way you're going to be able to write a closed form for it. Even if you could, you cannot write these derivatives out and equate them to 0, and it's just not going to be possible to solve for where this becomes 0. So in these situations, we need iterative solutions. We're going to begin with a guess for the optimal x and refine it iteratively till the correct value is obtained. So what we will do is we will start off with some initial value of x and say, here's where I think the function is a minimum. Then you check it out there and you look around and say, no, the function is not really a minimum, it's decreasing in some direction. So then you take a step in the direction in which the function is decreasing. You arrive at a new point, look around again, it's still not a minimum, then you take a step, hopefully in a direction in which the function is decreasing. And keep doing this till you arrive at a point where the function walking in any direction doesn't decrease the function anymore. Now, the problems here are, you're over here, which the function is not a minimum here, which direction must you step in for the function to decrease, and how big must the step be? Because if you miss on either of these, then you're going to mess up. So for a scalar function of a scalar variable, let's start with that. It's very easy. Now, let's go back to our figures. Suppose I have a function of this kind. This is x. I'm trying to minimize it. This is the function. And let's say the function is of this kind. I'm out here. I'm trying to minimize the function. What is the slope here? Is it going to be positive or negative? Anyone?
Negative.
It's going to be negative because it's decreasing, right? Which direction must I step in to go towards the minimum?
Right.
Right. So I want to go from x0 to x0 plus some delta x where delta x is greater than 0. Suppose the function is of this kind and I'm out here. So and this is what I must do when the function is decreasing. F prime of x is less than 0, right? If the function is of this kind, what's the slope, sign of the slope going to be here?
Yeah, positive.
Positive, right? So this f prime of x is greater than 0. If I'm out here and if I want to go towards a minimum, which direction do I go?
Left.
Now I'm going to go left, right? So over here you'd have wanted to go right. Here you want to go left. So then you want to say x0 goes to x0 minus delta of x, where again delta of x is greater than 0. So here are the two. If you want to go in the direction in which the function is decreasing, when the slope is negative, you want to increment x. When the slope is positive, you want to decrement x. And so we can have this very simple rule. You initialize with some x0. You check the derivative at that point. If the sign of the derivative is positive, that means it's an increasing function. Then you want to take a step backwards. So you say x equals x minus step. If the sign of the derivative is negative, it's a decreasing function. So you want to continue going forward. So you say x equals x plus step. How large the step must be is an issue we won't get to right now. Now, can you think of a way of writing this ugly thing in a more compact manner? In one line. Anyone? So here's what I've got. I have if sine of f prime of x is greater than 0, x goes to x minus delta of x. If sine is of f prime of x is less than 0, x goes to x plus delta of x. I want to write these two in one equation without an if statement. How would I write it? Anyone?
In chat, we have someone saying xk minus step times delta x.
So I can just write this as x equals x minus sine of f prime of x delta x, right? Observe, when sine is positive, this is going to become, this is a positive number, so you end up with this equation. When sine is negative, this is negative, negative and negative become positive, so you end up with this equation. Everybody see how that happened? I assume so. So I can compact these two lines into one equation. When the derivative is not 0, I'm going to increment x of x as x equals x minus the sine of the derivative times the step. I can compact it even further. We haven't specified the step. So instead of explicitly looking at only the sign, I can just use the derivative itself, because the derivative has the same sign as the sign of the derivative. So this too is going to be doing the same thing. When the derivative is negative, it's going to be going forward. When the derivative is positive, it's going to be going backwards. So this gives me this trivial algorithm. I start off with an initial point and then keep stepping in this manner till I get to an optimum. Now this has a very nice property. And what is that? If you have a nice function is going to look like so, right? It's got a nice goal with a nice, beautiful minimum. Then over here, what is the magnitude of the derivative going to be? Is it going to be large or is it going to be small? Anyone?
Large.
Large. So here at this location, do you want to take a big step or a small step?
Big step.
You want to take a big step because when the derivative function is steep, it means you're very far away from the minimum. So you want to jump all the way here, right? out here, is the magnitude of the derivative going to be large or small?
Small.
Small.
Small. What would happen if you took a large step?
You're gonna miss it.
You're going to go boom out here, right? So when the derivative is small, you want the step to be small. And so you want the step size to be somehow proportional to the magnitude of the derivative. Because for nice functions of this kind, when this is steep, you're far away, you want to take a big step. When it's shallow, you're close to the minimum, you want to take a small step, you want to walk very carefully. And so this update rule has this very nice property. And the same thing holds even if it's a multivariate function. I can just say that so focus on the minimum. I have a generalization over here for both maxima and minima. But then to find a maximum, you move in the direction of the gradient. To find a minimum, you move exactly opposite to the gradient, but the same rule holds. I'm just going to take some step size times the derivative itself, the gradient itself, the gradient is the transpose of the derivative, remember? So, and the gradient has the same dimensionality as x. So at each point, I'm going to take a step against the gradient and proportional to the gradient. So if I'm out here, if I'm trying to find a minimum, maximum, I'm going to be incrementing x in the direction of the black arrow, which will take me up. If I'm out here, I'm going to decrementing x, changing x in the direction of the red arrow, which is going to take me down. That's what this rule says. So you can keep doing this. When will you stop? Now you want to stop when you think you have a minimum. And there are two criteria. You can say, my function value isn't changing very much between steps. So you could stop. Or you could actually explicitly evaluate the derivative at the current point and say, oh, this has become 0. It's become really small. I think I'm near a minimum. I'm going to stop. And we'll see why this is a dangerous thing to be doing. This is really the only thing you must be doing. So here is the overall gradient descent algorithm. I'm just repeating myself. You initialize x, then iteratively increment, modify x by incrementing in a direction exactly opposite to the gradient, and keep doing this till the function doesn't change anymore. And this will work really nicely for functions of this kind. If you've got ugly functions of this kind, then you can get stuck in local minima, you can get stuck in inflection points, nasty things can happen. We will see what can happen in a couple of classes. Questions, anybody? Any questions?
Nothing on chat.
Okay, fine. So here's our problem statement again. We are given a set of training points. We've defined our loss function. We're back to training our neural networks. Our loss function is the average of the divergences at these training points. We want to minimize this loss with respect to W. This is an instance of function minimization. And so we're going to use the simple gradient descent rule. Why the gradient descent? Because you're always descending down the gradient, right? At each point, you're computing the gradient and you're descending down the gradient. So it's called the gradient descent rule. And we will use the gradient descent rule to optimize this. Now, before we continue, we're going to have to define a whole lot of things. Here are all the things we don't know. What are these input-output pairs? How do we represent them? What is this function f? What are these parameters w? What is this divergence? What function? To completely specify the loss function, all of these things must be specified. Otherwise, you're not going to be able to optimize it. So let's start with the simplest one. What is this function f? And what are its parameters? For us, the function is just a multi-layer perceptron. It's a directed network with a set of inputs. What we call the input units are not neurons, they're just inputs. And a set of outputs. And any input is processed sequentially left to right. We are going to assume no loops, as we mentioned in the last class. So it's a directed network. Now, In the standard setup, each of these individual neurons we're going to assume has the nature of a perceptron. It has an activation function which operates on an affine combinations of the inputs. So each neuron looks like so. It computes an affine combination of the inputs and applies an activation function to this affine combination, where the activation function is continuous and mostly differentiable. You might have cases like this guy who's not differentiable right at this hinge, but it's going to be continuous and differentiable. We saw why this is required. If it's not differentiable, then you cannot find out which way to adjust the parameters to improve the function. So this is the nature of the function we are going to assume, the parameters of the weights and the bias. But more generally, you can have any function of the inputs. We won't go into the general case. Now, here are some typical activations. We've seen the sigmoid before. The sigmoid has this equation. It's 0 at x at z equals minus infinity. It's 1 at z equals infinity. And it's varies smoothly between these two guys. And the sigmoid, of course, is going to have this property that because the sigmoid has this shape, the derivative out here is 0. The derivative out here is also 0. The peak derivative is at this point. So the sigmoid's derivative is going to look something like this, where the peak derivative is 0.25. So that's a popular activation function. The tan H is also an popular activation. That's basically just the sigmoid shifted so that it's centered around 0 and scaled. So the tan H now has, because it's scaled by a factor of 2, the peak derivative out here is going to be 0.5 rather than 0.25. Then you have these other activations. The ReLU, which is this guy. The ReLU is an interesting function. It is the ReLU is 0 out here. So let's say these are my axes. Then the ReLU is going to be 0 to this point, and then it's going to be exactly equal to x beyond this point. What will the derivative of this guy look like? Anybody?
Heaviside function.
It's a heaviside function. It's going to be 0 till here, and then it's going to be 1 at this point, right? So that's the derivative of the ReLU. Now this is nasty. Right at this point, we really don't have a clear definition of the derivative. So sometimes we like to use this softer version of the ReLU, which also goes to 0 at minus infinity, and it goes to f of z equals z, f of z equals z. For large values of z, in between it's the smooth curve for which you can actually compute the derivative. Take a look at the formula on the slides. I won't spend time on it. Now, you can also have neurons that have multiple coupled outputs. So here, now, in everything that we've seen so far, I've assumed that my neuron is, I have a neuron which computes some affine value, and then you apply an activation. So I have, for this guy, the activation function itself took in a single z and output a single y, right? So this one is a scalar function of a scalar variable. This is how we have been looking at neurons. But then I can have, so if I have a set of these neurons, each of these is going to have its own activation, Z1's affine combination, and each of these is going to have its own output. And now if I perturb this Z, these outputs will not change. I can have an alternate case where all of these Z's go into this magic box and Y's come out, a bunch of Y's come out. This is a more generic setting. And here, you cannot make an assumption that perturbing this Z will not change these outputs. Perturbing any of these Z's will change, in the most generic case, all of these outputs. So here, the correct way for me to write it is y1 through yn is some function of z1 through zn. So this is what I will call a vector activation, whereas this I will call a scalar activation. Now, and so you can also have vector activation of this kind. And now the property of this vector activation is this. When I compute these affine combinations, each of these affine combinations comes with its own set of weights. Now, in this case, if I change the weight of a connection going into this Z, it would not change these Y's. Here, if I change the weight of a connection going into this Z, it's going to change this Z, but because the Z changes all the Y's, changing this W is going to change all of the Y's. Do you see the difference between the two cases? Someone who didn't get it, raise your hand. Anybody who didn't get it? Okay. So one specific case that you encountered is the softmax. The softmax computed affine combinations of a collection of inputs. You got all of these Z's, and then you computed the corresponding Y's. The way you computed it is you exponentiated each of these Z's, but then you normalize the outputs to sum to 1. So here again, the parameters are the weights and the biases. But then if I change this W such that this Z increases, when this Z increases because of this exponentiation, this Y will increase. But because of the normalization and because all of them must sum to 1, correspondingly, the rest of the Y's will decrease. So a softmax is that vector activation. Now, before I continue, just a quick notation. I'm going to be, oh boy, I'm like 30 slides behind and 20 minutes to go. Now, here's how we are going to denote everything. I'm going to call the input layer the 0th layer, when the input layer really has no neurons associated with it. It's just the input to the network. We are going to represent the output of the ith neuron in the kth layer, like so. So at any neuron, you have two things happening. So you have all of these layers of neurons, right? And there are many, many of these guys. And then finally, you have some output neurons which produce outputs. Now, so here are all the variables corresponding to any neuron in, say, the kth layer. This is the kth layer. You have the weights coming in. Then you have the affine combination just before the activation is applied. And then you have the actual output of the neuron. So if I focus in on the neuron, I have all of these weights, which are added to give me a Z, and then comes an output Y. And this is from the kth layer. So I'm going to use this notation. I'm going to say Wij superscript K within parentheses. This means that it's referring to some neuron in the kth layer. Wij means that, firstly, it means that this is the jth neuron in the kth layer. This is the connection from the ith, this is the ith input to the jth neuron in the kth layer. The affine value itself I'm going to represent as Z, J of K. So this is the affine input to the jth neuron in the kth layer. The output is going to be Y, J, K. It's the output of the jth neuron in the kth layer. So this is the standard notation that we're going to be using through these lectures. And specifically because the inputs, the 0th layer is simply the input, then Yi0 is simply the ith component of the input. And the output of the network is simply the ith output of the network is simply the ith output of the final layer of the network. So this is just setting the notation. We'll revisit it when we go through the math. So what we've done is fully specified the function f. Now, what are these input-output pairs? These input-output pairs are, your inputs that you provide to the network and the target output, but then they must be numeric because the network is a numeric computation. So the input is going to be some vector. The notation uppercase X superscript n means it's the nth input, but each input is going to have a bunch of components. So in which case I'll have a small x. The first argument is the index of the input. The second argument is the component number. I will use the D to be the desired output of the network. So the desired output of the network in response to the nth input is also going to be an L component vector. And that's what these indices represent. Now, there are two different things going on at the network. One is what you want the network to actually output, and the other is what the network does output. So I'm trying to learn a function. So my training data says that in response to this X, I want the output to be the D, but for any particular setting of the parameters, I'm going to get a different output, which is Y. I'm trying to minimize the gap between these two guys. So the actual output of the network is going to, so the desired output of the network is going to be represented by D. The actual output of the network is going to be represented by Y. And very often I won't show you this first index and only show you the component index because we will be talking about individual inputs. So what are these? So this is just the representations again, but what are these values? These inputs, they have to be numbers. So they're vectors of numbers. They can be a vector of pixel values if you're working on images. They could be a vector of speech features if you're working on speech like you are doing in homework 1. Or if you're working in text, it's going to be some real valued vector representing the text. So now you have the sequence of words. You have to somehow magically convert it to a vector of numbers. And we will do so. We'll see how that happens in a later lecture. Now, so we've defined the input. What about the output? Now, if the desired output is real valued, then no special tricks are necessary. The output is simply going to be the actual value that you want to represent. If the desired output, if you're trying to compute a scalar function, the desired output is going to be a scalar. And if you're trying to compute a vector function, the desired output is going to be a vector of real numbers. On the other hand, if the desired output is binary, like in a binary classification task, then we can use a simple 1-0 representation to represent the desired output. And this, so here, for example, if I'm trying to say, is this a cat or is this not a cat? Then I would have an output of 1 for yes, this is a cat, and 0 for this is not a cat. In this case, there are two ways of thinking about this output value. You can think about the output value. So I've got an input of, which is a picture of a cat. It's gone into my network, and output comes out. And I want the output to be either 1 if this is a cat, and this is 0 if this is not a cat. I can think of these as a real number. It's either 1 or 0. Or I can think of this as the certainty that my network has that this is the cat. In the second interpretation, the network is saying the probability of cat equals 1. I'm absolutely certain that it's a cat. Or I'm going to say the probability of cat equals 0. I'm absolutely certain that it's not a cat. And you want the network to be very certain. So you're telling the network that when I give you a picture of a cat, I want you to be, this particular picture of the cat, I want you to be absolutely certain that it's a cat. If I give you this other picture, which is not a cat, I want you to be absolutely certain that it's not a cat. So there are two ways of looking at this target output, either as just numbers or as certainties, as probabilities. And this is the interpretation that we will actually use. And consequently, we will use a sigmoid activation over here. And the sigmoid output of the sigmoid activation is going to be a real number between 0 and 1. So the actual output of the network is going to be some number between 0 and 1, which is going to be the a posteriori probability of the target class given the input. And ideally, our desired output is that it should be strictly 0 or strictly 1. In reality, it's going to be something in between. And we're going to try to make the two match. Now, when I have multiple classes, if I'm performing multi-class classification, then I'm going to have things like these. I'm going to be trying to distinguish between objects like a dog, a cat, a camel, a hat, or a flower. In this case, we will represent this set as a ordered set, as a vector of this kind: cat followed by dog, followed by camel, followed by hat, followed by flower. Now, if I have an input which is a cat, I'm going to represent it as this vector, which has a 1 in the first location and zeros elsewhere. So observe that it has a single 1 and zeros elsewhere. If the input is a dog, then my target output, my desired output, is 0 in the first location, 1 in the second location, the location of the dog, and zeros elsewhere, and so on. Now, these vectors are what are called one-hot vectors, because it's a bunch of zeros and only one element is hot. And these vectors too can be thought of as the probabilities of these classes. If I present the network with a picture of a cat, I want it to be completely certain that it's a cat, and I want it to be 100% certain that it's not a dog, a camel, a hat, or a flower. So this too represents the ideal probability distribution that is output by the network. And so when I have a multi-class classification task, the network is going to output as many outputs as the number of classes I have. But what it is actually going to be outputting is the probability for each of these classes. And the ideal output is this one hot vector. Now, so for a multi-class classifier with n classes, you will basically have the one hot representation is going to have the desired output is going to have n binary values. The network's output also must ideally be binaries, n minus 1 zeros and a single 1 in the right place. More realistically, it's going to give you a probability distribution that's not so perfect. And we are trying to, and the business of training the network is to try to make the output as perfect as possible. I have no idea how the rest of the picture disappeared here. So what about the actual output of the network? In the case of the multi-class classification, the output is going to be the softmax. And the softmax we saw is a probability distribution. This is going to be a set of numbers whose values sum to 1. And for a given class, we want to adjust the parameters such that this becomes as close to being a perfectly certain probability distribution, a one hot vector corresponding to the class. And so in a typical problem statement, you're given a bunch of training instances, images of digits along with information about which digit the information represents. So in a binary recognition task, it will be, is this 0 or not? In multi-class, it's going to be which digit is it? So for binary classification, your training data is going to look like so. These are the inputs. Corresponding to each input, you will have a binary label. And the network will have a sigmoid output. We're going to try to train the parameters of this network to produce these outputs. For a multi-class classification task, you're going to, you would add the target output is going to be a one hot vector, but you don't actually have to explicitly represent it as a one hot vector. One compact way of saying, of representing it is saying this is a one hot vector where only the fifth component is 1. This is a one hot vector which is only the second component is 1. Regardless, basically eventually the target output is going to be one hot and the actual output is going to be a probability distribution. And so we've sort of defined what this function is and what these guys are. I'm going to spend 5 or 6 minutes going over the divergence. Please stay with me if I go a little over. Any questions about what we've done so far? If you have any question, if you have any questions, let's also take it to Piazza. First thing, the last component that we have to define is the divergence, and for the loss to be differentiable with respect to W, the divergence must be differentiable. We saw that if the activations are differentiable, then we will know how changing any component of W by a small value changes F. But then you also want to be able to compute how changing F by a small amount changes the divergence. Otherwise, you cannot minimize this. You cannot compute the derivatives of the loss with respect to the components of W. So this divergence function too must be differentiable. Only if it's differentiable will you be able to say, okay, how much does a small change of W change the divergence itself? This is critical. Now, what kind of divergence functions can we have? If my output is real valued, then a typical divergence function is between the actual output of the network and the target output of the network can simply be this Euclidean distance between the two. So if the output is scalar, it's going to be just, if the output is a vector, it's going to be half of the Euclidean distance. Half is just a term of convenience so that we can differentiate this divergence and the twos cancel out. And so it's going to be the sum over all components of the square of the differences between the actual and target outputs for the network. And if you actually differentiate this guy, you're just going to get, if you just work it out, the derivative is a row vector, which is the row vector of the derivatives of this guy with respect to the individual components of y, which is going to be just this term over here, right? The first one is, the first term is the first output minus the desired first output. The second one is the second output minus the desired second output, and so on. And now observe something over here. These are just the errors. So when the output is real valued and the target output is also real valued, then the derivative is a vector of errors between the actual output of the network and the desired output of the network. This looks a whole lot like the kind of, and now our update rule itself looks something like this, right? WK plus 1 equals WK minus Y minus D, YI minus DI. This is the component times eta. You'll observe this looks a whole lot like the perceptron learning rule. You're adjusting each weight in proportion to the error made by the perceptron. So this has a very nice interpretation, which links back to the perceptron rule. For binary classifiers, this is the last thing we will do today, so stay with me. I have a couple of different ways of thinking about it. Now remember, when I'm classifying, so what we saw earlier is when, in the previous slide, was when we are trying to make real valued predictions. So this is what we use the Euclidean distance, L2 divergence, when we are trying to make real valued predictions. But if I'm trying to predict the, if I'm trying to perform classification, the output is not real valued. Consider the case where I'm back to this case of, is this a cat or is this not a cat? The output is going to be either 0 or 1. The desired output is going to be either 0 or 1. The actual output of the network is going to be some number between 0 and 1. We have two ways of looking at this. I can look at both of these as just real vectors, real values that I'm predicting. If I look at these as real values that I'm predicting, then the obvious error is going to be y minus d whole square. This is my L2, right? And this will be 0 then when y equals d. But this is missing a very important point. It's missing the point that this is a classification task, and this is really not what we want to be doing. So if you think of this as a probability, you know, look at this guy. If my desired output is 0, so I want the network to be 100% certain that this is not a cat. And if my actual output is 1, the network is 100% certain that this is a cat, then getting an error of just 1 is a terrible thing to be doing. I'm infinitely wrong. I'm exactly opposite of what I want the output to be. So what you really want is a divergence function which tells me that when the desired and the target outputs are in exact opposition to one another, this error is intolerable. This is infinitely wrong. And your standard L2 divergence does not capture this property. Here, when the two are in exact opposition to one another, you still get a finite error. So instead, we will use the Kullback-Leibler divergence. The Kullback-Leibler divergence, I'll just give you the formula over here, is going to be minus, this is when you're making a single binary prediction, is going to be minus d log y minus 1 minus d times log of 1 minus y. So when the desired output is 1, 1 minus d becomes 0, so this term goes away. When the desired output is 0, this term goes away. You're just going to be 1 minus d is 1. So the output is going to be either log y. The divergence is going to be either log y or log of 1 minus y. Now to see why the Kullback-Leibler divergence differs from the L2 divergence, let's take a look over here. This is for the binary classification task. In this case, my desired output is 0. And y is the actual output. I'm showing this over here. If I were using the L2 divergence, then this is how the divergence changes with y. And you can see that when the network is completely wrong, the error is finite. But the KL divergence, because it's taking a look at log of y, in this case, log of 1 minus y, because d is 0. When y is 1, the divergence is going to be infinite. So the Kullback-Leibler divergence is like this. It's telling you that you're infinitely wrong when your prediction is exactly opposite to what it must be. And so, which is why this is a much better divergence to be using than this guy. And now if you're doing any kind of gradient descent, when you're infinitely wrong, you're going to take very large steps to get towards this minimum. Whereas if you were using the L2 divergence, you would not. This is the same plot when the desired output is 1. This is what this is the Kullback-Leibler divergence versus the L2 divergence. And again, you can see the L2 divergence doesn't encourage moving towards the correct solution as much as the KL divergence. And as a final point of note today, there's something very strange going on here. At the minimum, the L2 divergence has a derivative that's 0. At the minimum, the KL divergence has a derivative. The slope is not 0. The function continues to, at this point, the function has a slope that's non-zero, which means simply looking at the derivative to decide if this is a minimum is not going to work. So I'll stop right here. We'll pick up from right here on Wednesday. If you have any questions, I've run over, so post on Piazza. One last poll. Okay, so let's. The second one is right. The gradient of the loss may be 0 or close to 0 at a minimum, like in the case of the L2 divergence. But the gradient of the loss may also have a large magnitude at the minimum in the case of the Kullback-Leibler divergence. So simply looking at the magnitude of the gradient is not a satisfactory condition, because at least for the Kullback-Leibler divergence, which you guys are familiar with as the cross entropy loss, the derivative of that loss is not 0 at the minimum. We'll stop here and we'll pick up in the next class. Thank you, everybody. Please stop recording, guys.